Hello and welcome to my YouTube channel. In this playlist, we are trying to cover the operational amplifiers. Today I am going to talk about one of the most important properties of any operational amplifier, and that is virtual ground property. There are many books which are discussing about this particular property of an op-amp, but I will try to go a bit more deeper into this particular topic and try to clear some of the doubts which I had when I was studying about op-amps. So let's start the video. So this is going to be a very short video which is basically for discussing the virtual ground property of operational amplifiers. So let's start. First question is, what is virtual ground property? So there are two words here again. Virtual means which is not real, okay, which is not real, but it is almost real. Almost real. That means it is almost identical to reality. Ground, in electronics, ground means 0 volt in general. So the term virtual ground is made up of two words, virtual, which is almost identical to ground. But is it a correct terminal, or shall we look at this terminal in a different way? So first of all, according to virtual ground property, the voltage at inverting terminal, which we are defining at minus or V minus, so the voltage at inverting terminal will be almost equal to the voltage at non-inverting terminal, that is V positive. But remember this thing, that vice versa is not allowed at all. So let me tell you about this particular line. Vice versa is not allowed. But before that, remember V inverting will be almost equal to V non-inverting. What does that mean? It means V plus, which is represented by pin number 3, V minus, which is actually pin number 2. Okay, so this is your V or voltage, non-inverting voltage. Pin number 2 represents inverting voltage input. So according to virtual ground property, the voltage at pin number 2 will be almost equal to the voltage at pin number 3. So remember, voltage at inverting terminal is equal to voltage at non-inverting terminal, but vice versa is not allowed. That means voltage at non-inverting terminal will not be equal to the voltage at inverting terminal. This might be very confusing, because when we are saying both are equal, why not we apply the same principle to the non-inverting terminal? I will go deeper into this topic. So remember, this is very important. In most of the books, we study about virtual ground property, and they talk only about that the inverting and non-inverting terminal are short. Okay, rather I would prefer to call, rather than calling it virtual ground, I will prefer to call it virtual short. I will talk about this property because it is not necessary that it will be always virtual ground. For some derivational part, most of the people talk about virtual ground, but for me, or I prefer to call it virtual short, and keeping the above properties, that V minus equal to V plus, but V plus is not equal to V minus. Let me elaborate on that particular line. So I am going to show few simulations by which I will try to clear the concept of virtual ground. First of all, here I have designed an amplifier, which is an inverting amplifier. Why? Because voltage is connected, or which is provided to pin number 2, whereas pin number 3 is grounded. So because the input voltage is provided to pin number 2, it is called inverting amplifier. later in the coming videos I will discuss about how to design amplifiers, how to analyze the amplifiers and all. So here I have a voltage source which can go up to 100 millivolt maximum, but this voltage source is variable. So I have connected probes at the input voltage, then at the junction of pin number 2 resistance R1 and feedback resistance R2. So this is our junction terminal. Then I have connected one probe at pin number 6, which is our output, and another probe at pin number 3. So let us try to simulate this particular circuit. Here you can see the voltage at pin number 3 is 0 volt because it is directly connected to ground, whereas the voltage in pin number 2 is 1 millivolt. And what is the voltage applied to the resistance R1? It is 40 millivolt. So we are providing 40 millivolt, but at pin number 2 we are getting 1 millivolt, whereas pin number 3 is 0. So we can call that pin number 2 is almost equal to 0. And now you may say, if I change the input voltage V1, then definitely the voltage at pin number 2 will also change. Let us check. So I am going to increase it to 0.8 volt or somewhere around 0.8 volt. But still you can see the voltage at pin number 2 is constant, that is 1 millivolt, which is almost equal to the voltage at pin number 3, which is grounded, 0 volt. So 1 millivolt can be neglected, or we can call it 0 volt. So indirectly we can say pin number 2 and pin number 3 are short circuited, and the voltage at pin number 2 is equal to the voltage in pin number 3. So this is why I was calling it virtual short rather than calling it directly virtual ground. But otherwise you can see, even if I change the input voltage by any value, I am still getting the same voltage, which is voltage at pin number 3. So pin number 3 is 0 volt, pin number 2 is 1 millivolt. Let me slowly gradually change it again. You can see, even though I change the voltage at the input, the voltage at pin number 2 remains almost constant, and which is almost equal to pin voltage at pin number 3. So let us go to the another circuit where I show you a different circuit where the input is provided to pin number 3. So this is non-inverting amplifier. Why? Because the input is provided to non-inverting input. Pin number 2 is grounded via R1, which is 1 kilo ohm, and it is it is connected to R2, and R2 is connected to pin number 6. R2 is 10 kilo ohm. So let us simulate this design. Here you can see the input voltage is 24 millivolt at pin number 3, and you can see pin number 2 is 25 millivolt, which is almost identical to pin number 3. Let me change it again. So here I am applying 66 millivolt, and at pin number 2 I am getting 67 millivolt. Although you can see there is no voltage directly connected to pin number 2, only the feedback voltage which is coming from pin number 6. So even if I change these voltages, you can see I am applying 90 millivolt at pin number 3, and I am getting 91 millivolt at pin number 2. So this is virtual shorting. So pin number 2 is again getting the same voltage which is present in pin number 3. Although it is not grounded, pin number 3 is not grounded in this case. So rather calling it virtual ground, I would prefer to call it virtual short, because whatever the voltage is present in pin number 3 will be almost shifted to pin number 2. Okay, so now coming to the last question, that when I was saying the voltage at pin number 2 will not be equal to the voltage at pin number 3. Let us check that thing. Here what I am doing is I am applying an input to pin number 2 via R1, and pin number 3 is not directly grounded here. Remember, the pin number 3 is not directly grounded, rather it is connected via 1 kilo ohm resistance. So let us check the voltage at pin number 3 and pin number 2. You can see here the difference. Pin number 2 is having 991 microvolt, whereas pin number 3 is having 56 microvolt. So it is not getting the voltage which is at pin number 2. So pin number 2's voltage is not shifted to pin number 3. So you might say, okay, so why the pin number 3's voltage is not present in pin number 2? For that, what I can do is just remove this particular component. Let me keep it here and just connect another input source to pin number 3. So now I am applying two inputs. One is at pin number 2, which is V1, and applying another voltage source V2 at pin number 3. This configuration is called differential input configuration because we are applying input to both the pins 2 and 3. Remember, when we apply input to pin number 2, we call it inverting amplifier configuration. When we apply input to pin number 3, then we call it non-inverting amplifier configuration. And when we apply input to both the inputs pin number 2 and 3, we call it differential input mode or differential amplifier mode. We will come to that topic later in the coming videos. Before that, now V1 and V2 both are there present in pin number 2 and 3, and I will try to simulate it. So here you can see pin number 3 is getting 880 millivolt, which is directly connected to pin number 3. And now you see here pin number 2 is getting 881 millivolt, which is almost identical to that of pin number 3. So let me change the voltage at pin number 3 and see here, if I change it to 0.12 volt or 120 millivolt, you can see here at pin number 2 we are getting 121 millivolt. So if I change the input at pin number 2, that is the voltage source V1, what will happen? Let me change it. Now I am applying 0.8 volt to pin number 2, but still you can see the voltage at the pin number 2 is almost identical to the voltage at pin number 3, which is 120 millivolt. Almost identical. So it will not, that means the voltage at pin number 2, which is V1, it is not significantly changing anything at the junction of R1, R2 and pin number 2. The voltage is always constant and it is equal to the voltage at pin number 3. So let me repeat it. The voltage at pin number 2 will be always equal to the voltage at pin number 3, but vice versa is not allowed. I hope this video will give you some insight about the virtual ground property. Rather than calling it virtual ground, prefer to call it virtual short. With this, I would like to end this video. I hope you like this video. If you have any doubts or suggestions, please put your doubts or suggestions in the comment section. And if you have not subscribed the channel, then I would request you to please subscribe my channel. Thank you and have a nice day.